Hello, everyone. Thank you for joining today. I was given the opportunity to explain the results of analysis and simulation of the spread of COVID-19 in Indonesia using CRFV modeling with optimization. This is my presentation agenda today, which consists of 4 parts. First is introduction. So, COVID-19 is one of the viruses that causes disease in humans and animals. This disease causes moderate or severe respiratory tract disorders. The method of transmission of this virus is found to be through various media or intermediaries within a fairly short radius of infection. As of June 14, 2022, there are a total of 6,056,017 confirmed cases of COVID-19 infection in Indonesia, spread across 34 provinces. The cases are divided into several categories based on the condition of each individual, namely cases that are still active or under treatment, recovered, and died. A total of 0.05% were confirmed to be active, 97.36 were confirmed cured, and 2.59% were confirmed dead. Despite a significant decline after the completion of wave 3 of the Omicron, as of Tuesday, June 14, 2022, Indonesia reported 930 daily cases of COVID-19 infection. The last time Indonesia reported daily cases higher than this number was on April 13, 2022, within 1,551 new cases at that time. As such, Indonesia has recorded more than 500 daily cases for 8 consecutive days. Of course, this increase needs to be our common concern because if it is not mitigated properly, cases can continue to increase. However, recent cases reported by Indonesia are still lower than some neighboring countries, especially considering Indonesia's population is larger than other countries. This increase in cases can be influenced by several aspects such as increased population mobility, community activities that have returned to normal, and the implementation of health protocols that are starting to loosen. The current increase in cases needs to be suppressed as much as possible, considering that Indonesia has managed to maintain a decline in cases for 2 consecutive months and also knows if the impact of the spread of the COVID-19 virus has a fairly visible significance in Indonesia. Not only the health sector, but various other sectors are also affected, such as the economy, transportation, and tourism. It would be a shame if the spike in cases had to happen again. The mathematical model that will be used in this final project is CRFV. It will explain its development one by one, starting from CR modeling. This model divides the analysis population into 3 different compartments, namely S, susceptible, I, infected, and R, recovered. Then the second is CRF modeling. The initial 3 states are the same with the addition of the F compartment, Fadhl. The last is the CRV modeling. The susceptible, infected, recovered, vaccinated. This model is an extended CR model that takes into account the vaccination of the susceptible population. The following is an illustration of the relationship between the mathematical model of one compartment with the next compartment. In the picture, the CRFV modeling is described, which contains 5 compartments, namely S, susceptible, which is a person who is susceptible to COVID-19. I, infected, is a person infected with COVID-19. R, recovered, is a person who has recovered from COVID-19. F, fatal, are people who died from COVID-19. And V, vaccinated, are people who still have immunity from COVID-19. When a new person is born, there will be an increase in the population. Here it is assumed that newborns will automatically enter the susceptible compartment, namely people who are susceptible to COVID-19. This is because newborns do not yet have immunity to avoid COVID-19. Here, the birth rate is represented by the notation alpha. Because COVID-19 is a virus, it will spread through contact with infected humans. In the figure, it is illustrated that if the population in the susceptible compartment is in contact with the population in the infected compartment, it will be infected. Here, the contact rate with an infected person will be described by the notation beta. The population in the susceptible compartment, if it has been vaccinated, will move to the vaccinated compartment population. It will not be a person who is susceptible to COVID-19. The rate at which susceptible persons are vaccinated will be represented by the notation delta. The population in the susceptible compartment can also die. In this case, it means that it died naturally, not due to COVID-19. Here, the death rate outside of COVID-19 will be described with the notation mu. The population in the infected compartment, in addition to being able to the beta rate, it can also decrease due to people dying. In the case of the population in the infected compartment, death cases can be divided into two types, namely natural deaths, excluding COVID-19, and deaths due to COVID-19. Here, the death rate outside of COVID-19 will be described with the notation mu, while the death rate caused by COVID-19 infection will be described with the notation sigma, and will enter the population of the fatal compartment. Besides being able to decrease due to people who died, the population in the infected compartment can also be reduced due to people who have recovered from COVID-19. Here, the recovery rate will be described by the notation gamma, and will enter the population of the recovered compartment. The population in the recovered compartment can still die naturally beyond the cause of COVID-19, so here it will be described with mu notation. Vaccination has a period of time because the way vaccination works is to form antibodies so that a person can be immune from a disease, and after vaccination, the body will form IgM antibodies or immunoglobulin M, which are antibodies that are formed earlier after being infected with COVID-19. After vaccination, there is a period of time during which the level of IgM in the body is still sufficient to protect a person from the related virus. When the IgM level is zero, so no longer has antibodies, the population in the vaccinated compartment will return to the susceptible population, which will again be susceptible to the COVID-19 virus. This means that after a person has received a COVID-19 vaccination, they are expected to use a booster periodically. The rate of population change from vaccinated to susceptible will be described by the notation rho. So at some point, depending on the resistance of the vaccine, someone who has been vaccinated will again become susceptible to the COVID-19 virus. This is not known specifically. There are many variables that can influence, such as the type of vaccination, the variant of the COVID-19 virus exposed, etc. In addition, people who have been vaccinated can also die naturally beyond the cause of COVID-19, which is described by mu notation. One of the parameters that represent all other distribution parameters is the basic reproduction number, or R0. The basic reproduction number, or R0, is often used as a threshold parameter to determine the boundary between extinction and the spread of a disease. This parameter is also important to see the continuation of the trend of the spread of the COVID-19 virus. A value of R0 below 1 means that each infection stream will produce less than one other infection, which indicates the pandemic will end quickly, and vice versa. For R0 above 1, each infection stream will produce more than one other infection, which indicates the pandemic will continue. So from the results of previous literature studies, it was found that the emergence of the COVID-19 pandemic in Indonesia, which then caused various problems to arise, such as in the health, economic, social fields, to the stability of a country's development. Based on these problems, one approach that can be used to understand the spread of disease is to use mathematical modeling. One type of mathematical modeling that can be used to understand the spread of epidemic diseases is the CRFV model, which is a derivation of the compartmental model concept proposed by Carmack McKendrick. In general, this modeling concept divides the analysis subject population into several groups based on their health status. In the CRFV model, These groups are susceptible, infected, recovered, vaccinated, and fatal. This is then reduced to 3 problem formulations as follows. Based on the formulation of the problem that has been formulated, the purpose of compiling this final project is to develop a model with an optimization concept for the analysis of the spread of COVID-19 in Indonesia with the CRV concept. To simulate scenarios for the spread of the COVID-19 virus in certain scenarios based on the concept model CRV, and evaluate the performance of the optimization concept when applied to the analysis of the spread of COVID-19 in Indonesia with the CRV concept. In the preparation of this final project, there are several limitations that are determined. The first scope and limitations that will be studied are the collection of data on the spread of COVID-19 disease in Indonesia from the Our World in Data dataset, Kawal COVID, and the COVID-19 Task Force website at covid19.go.id. The modeling is done by dividing the spread time into 73 phases to estimate the distribution parameters of each. The phase division is based on the CoVID library, mathematical modeling of the spread of the disease using the CRV model, and the optimization algorithm is implemented using the Python 3 programming language. The hardware used is Alice's personal computer with specifications as follows: model development and optimization using Google Colab and Jupyter Notebook platforms. The methodology used in the preparation of this project is Cross-Industry Standard Process for Data Mining, or CRISP-DM. This model will explain and provide an overview of the cycles and what stages will be carried out from a data mining project. This method is used as a methodology in the preparation of this project because it is one of the best practices that can be applied. Altogether, there are 6 processes described in this model. The processes are illustrated in the following figure. We enter the parameter estimation. So the following is a visualization of Indonesia's active cases since the beginning of the pandemic in March 2020 to June 2nd, 2022. It can be seen here that there are increases and decreases. Therefore, we suggest that parameter estimation is not only a set of parameters for a data set, but also a trend. At the same time, one set of parameters will be estimated in order to get a better estimation. So the trend is taken from the SR trend analysis. The following figure shows the SR trend of COVID-19 in Indonesia until June 2nd, 2022. The SR trend tends to decrease over time, which shows an inverse relationships between the susceptible and recovered compartments in accordance with the theory of the compartment model. Based on the CoVID SR trend, there have been 72 phases plus the initial phase or phase 0 with different durations. Each phase has its own time range and spread parameters, and the shortest phase consists of 7 days, while the longest phase consists of 14 days. Next, we will estimate the distribution parameters per phase. Based on the phases obtained in the previous section, several parameters of the CRV model will be estimated. Parameter estimation will be carried out using the concept of optimization using the Optimizati library, which is to perform optimization and search for the most optimum parameter value, which has the smallest error value as an objective function. In this experiment, the mean absolute percentage error or MAPE evaluation metric is used as an objective function. The smaller the MAPE value, the closer the difference between the actual data and the estimated or predicted data will be. There are also non-optimized parameters such as birth rate and natural death rate. The figures obtained are from World Bank data. After estimating the parameters, the results obtained in the form of a history of the spread of the CRV model virus parameters as of June 2nd, 2022. R0 is 1.04, which indicates COVID-19 cases are still rising slowly. It can be seen that the value of R0 experienced a significant increase in the third wave of COVID-19 with a maximum value of 4.107. This also indicates an increase in the spread of COVID-19. It can also be concluded that the spread of wave 3 tends to be faster than the wave 2 and wave 1. At the beginning of the pandemic, the R0 value was high at 3.01 because there were still many individuals who were susceptible to infection. This is because no individual has been infected or immunized naturally or through vaccination. When compared with active cases in Indonesia, it can be seen that in general, the value of R0 will increase in the phase when active cases also increase, and vice versa will decrease in the phase when active cases also decrease. Also, looking at the contact rate history graph, it can be seen that the pattern of development of the contact rate value is still at a dynamic level from time to time, depending on government policies, implementation of health protocols by the community, etc. When compared with the history of R0 in the figure, it can be seen that in general, R0 or reproduction number and contact rate correspond and tend to have the same pattern. This is because the contact rate is directly proportional to R0. However, the fluctuation of reproduction number is not only influenced by contact rate, but also other parameters such as vaccination rate, fatality rate, recovery rate, and vaccination decay rate. Looking at the recovery rate history, which explains the country's ability to handle cases of COVID-19 infection, there is a dynamic pattern as a result of the spike in infection cases, and it can be seen that most are at 0.07 to 0.3 according to the time to recover from COVID-19, namely 3 to 14 days. Looking at the history of the fatality rate or sigma, there was a spike throughout January to April 2021, which is the peak period of the COVID-19 wave 1 pandemic, and throughout June to July 2021, which is the peak period of the COVID-19 wave 2 pandemic. What's interesting here is that during the Omicron period or wave 3 of COVID-19, the fatality rate is relatively low. This means that although the spike in cases that occurred in wave 3 of the Omicron was among the highest, the number of the deaths that occurred was low. Looking at the initial immune history that explains the number of initial vaccinated compartments, it can be seen that the trend is increasing over time as a result of the increasing number of people being vaccinated. Now we go to results and evaluation. Based on the results of the evaluation, the CRV model is feasible to be used as an alternative to modeling the epidemic disease compartment. This can be seen from the value obtained from the following metrics. The coefficient of determination or R2 score is 0.7971. This shows that all independent variables simultaneously have an effect of 79.71% on the dependent or bound variable, while the remaining 20.29% is influenced by other variables not tested in the study. The results obtained can also be categorized as strong because it is more than 0.67 and not overfitting because it is not more than 0.95. The RMSE, root mean square error, and RMSLE, root mean squared logarithmic error, values are smaller and closer to 0 compared to CIR, CIR-D, and CIR-F modeling. The mean absolute error value is smaller and closer to 0 compared to CIR and CIR-D modeling. The mean absolute percentage error value is smaller and closer to 0 compared to CIR, CIR-D, and CIR-F modeling. For model simulation, it is divided into 3 major scenarios, namely simulation using the last phase parameter for the next 60 days, simulation based on several scenarios by manipulating contact rate, and simulation based on vaccination rate manipulation. A simulation of the spread of COVID-19 in the future will be made based on the following restrictions. The scenario development will use CRV modeling to estimate the infectant threat. The dispersion parameters used in the simulation will follow the dispersion parameters of the last phase or 72nd phase. The dataset used is limited to June 3rd, 2022, and simulations will be limited to August 1st, 2022. This is because maximum prediction of the next 60 days from completion of phase 72 on June 2nd, 2022. This is done by considering that parameter changes will always change dynamically so that the simulation time range is made quite short. The following is a simulation visualization using the last phase parameters for the next 60 days. The last phase parameter has an R0 value of 1.04, so that even though Indonesia seems to be at the end of wave 3, the infected compartment trend will still rise slowly. Actual data is marked with a blue line. Estimated active cases are marked in orange, and predicted active cases for the next 60 days are marked in green. Assuming that the parameters do not change for the next 60 days, it is predicted that there will be an increase in active cases from 2,997 cases as of June 3rd, 2022 to 3,412 cases as of August 1st, 2022. First, the contact rate manipulation will be carried out in real life. One of the things that can be used as a benchmark for contact rate is the health protocol as one of the government policies. So far, the government has issued policies that are closely related to minimizing contact between people to suppress the spread of COVID-19. However, recently the government has also begun to relax several policies such as removing masks outdoors and not limiting the capacity of public facilities. Thus, the purpose of simulations based on contact rate manipulation is to estimate the impact of tightening or relaxing policies related to health protocols. The first contact rate manipulation uses the average contact rate of 72 phases, obtained by an increase in the contact rate of 52%. The trend of active cases in Indonesia will tend to increase until August 1st, 2022. In this case, R0 is worth more than 1, which means there is an increase in cases. Following the trend of active cases in the last phase, if the contact rate is 152% initially, active cases will increase and reach the maximum value on August 1st, 2022, which is 68,246 cases. In this scenario, R0 is 1.6, which indicates that COVID-19 cases in Indonesia will increase until August 1st, 2022. Then the second manipulation of the contact rate using the smallest contact rate of 72 phases. With a significant decrease in the contact rate, the trend of active cases in Indonesia will tend to decline sharply until August 1st, 2022. In this case, R0 is also less than 1, which means there is a decrease in cases. In this scenario, active cases will tend to decrease from beginning to end and reach the minimum number on August 1st, 2022, which is 83 cases. In this scenario, R0 has a very small value of 0.36, which indicates that COVID-19 cases in Indonesia will decline sharply until August 1st, 2022. Then manipulate the contact rate using a largest contact rate of 72 phases with a 330% increase in the contact rate. The trend of active cases in Indonesia will increase sharply until August 1st, 2022. In this case, R0 is greater than 1, which means there is an increase in cases. In the scenario, active cases will increase exponentially, and if there is no change in parameters at all, active cases will reach more than 100 million cases on July 13, 2022, and will fall again to 37 million cases on August 1st, 2022. As soon as contact rate rose significantly, we could generate a new wave with a narrow time difference. In this scenario, R0 is 4.56, which indicates that COVID-19 cases in Indonesia will increase rapidly. However, based on the previous assumptions and limitations, these scenarios can only be used as comparisons and evaluation materials because the deployment parameters will always change and be dynamic. In fact, the outcome of the scenario in the next 60 days is very likely to change following the uncertain dynamics of the pandemic. However, it can be concluded that within the 60-day period, if health protocols are applied to reduce contact, active cases will tend to decrease. However, if the health protocols are not implemented, it is possible that a new wave of COVID-19 will return if no further action is taken to suppress the spread. From the following figure, it can be seen that until the latest data was taken, namely June 2nd, 2022, the number of vaccination recipients in Indonesia reached 72.5%, or as many as 200,327,327 1,825 of the total population of Indonesia, which is around 270 million people. In addition, as many as 167,507,245 residents, or 60.6%, have received the second dose of vaccination, and 37,458,813 residents, or 13.5%, have received booster vaccinations. The first vaccination rate manipulation used the mean vaccination rate of 72 phases, with a decrease in vaccination rate of 87%. The trend of active cases in Indonesia will tend to increase until August 1st, 2022. In this case, R0 is more than 1, which means that there is an increase in cases. It can be seen that in this scenario, COVID-19 cases in Indonesia will increase for the next 60 days. If there is no change in parameters, active cases are estimated to reach 648,143 as of August 1st, 2022. In this scenario, R0 is 2.05, which indicates that COVID-19 cases in Indonesia will increase until August 1st, 2022. Then the second manipulation of vaccination rate using the smallest vaccination rate of 72 phases, with a decrease in vaccination rate by 100%, or it can be said that vaccination is not carried out. The trend of active cases in Indonesia will tend to increase sharply until August 1st, 2022. In this case, R0 is more than 1, which means there is an increase in cases. In this scenario, it can be seen that active cases will continue to increase, and it is estimated that as of August 1st, 2022, active cases will reach 4,140,105, assuming other parameters are the same as the parameters of the last phase. In this scenario, R0 is 2.41, which indicates that COVID-19 cases in Indonesia will increase until August 1st, 2022. The manipulation of vaccination rate using the largest vaccination rate of 72 phases with a fixed vaccination rate, the trend of active cases in Indonesia still tends to increase slowly until August 1st, 2022. In this case, R0 is more than 1, which means that there will be an increase in cases. It can be seen that active cases will decrease, and it is estimated that active cases will increase to 3,353 on August 1st, 2022. Assuming other parameters are the same as the parameters of the last phase. In this scenario, R0 is 1.04, which indicates that COVID-19 cases in Indonesia will increase until August 1st, 2022. However, just like the simulation of health protocols based on previous assumptions and limitations, these scenarios can only be used as comparison and evaluation material because the deployment parameters will always change dynamically. What is quite unique is that the 3 cases still produce a reproduction number of more than 1, which means that cases will continue to increase. It can be seen that the tightening and loosening of vaccination rates have no significant effect on each other. In fact, the maximum vaccination rate of 0.75 is still not enough to reduce active cases following the trend of the previous phase. It can be concluded that within the period of 60 days, vaccination alone is not enough to reduce cases. In addition to vaccination, it turns out that one of the other control parameters, namely the health protocol, is allegedly playing an important role. Vaccination alone, without implementing health protocols, will not automatically make the trend of active cases decrease. Vaccination cannot be completed only once because the CRFV model also considers the characteristics of the vaccination itself. Vaccination is, after some time, the antibodies formed in the rate of vaccination will drop, so you will need another booster. So the vaccination here is not only the first vaccine, there must be a continuous booster to maintain the antibody. Because if there is no booster, the vaccinated will be susceptible again. Now we go to conclusions and suggestions. From the results of the study, several conclusions can be obtained as follows. The CRFV susceptible infected recovered fatal vaccinated model has been created with parameter estimates to model the dynamics of the spread of COVID-19 in Indonesia. The modeling is done by dividing the spread time into 73 phases to estimate the distribution parameters of each. Parameter estimation is done by fitting the actual data of active cases as infected compartment. An evaluation has been carried out in modeling the dynamics of the spread of COVID-19 in Indonesia using several evaluation metrics. Based on the results of the evaluation, the CRV model is feasible to be used as an alternative to modeling the epidemic disease compartment. This can be seen from the value of the evaluation that has been carried out. And after the simulation, it can be concluded that the application of health protocols represented by the emphasis on contact rates can reduce cases. On the other hand, the implementation of a vaccination program can have an effect on reducing cases if it is accompanied by health protocols. The following are suggestions that the author can give to improve the quality of this final project or to continue other similar studies. Combining the CRV model with other model structures such as SEIR, SIRS, so as to produce a model that is more representative of compartments in the real world, fitting not only with the actual data of active cases for the infected compartment to produce a more accurate parameter estimation, and increase the number of trials and narrow the boundary in estimating parameters to make it more accurate, fitting with data from other countries for comparison, and fitting not only with the overall data of Indonesia, but also with regional data so that it is more widespread and representative. That's all from my presentation, more or less. I apologize. Maybe if there are questions or good suggestions from you, please reach out to one of our email. Thank you.